Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to describe or answer the question, what is a derivative and how is it calculated? And for this discussion, first we're going to take a look at the function y equals x squared. And I'm going to draw just a quick sketch of this function over on the left here. Now y equals x squared is a parabola, opens up, centered at 0, 0. So the graph is looking something like this. And hopefully we're familiar from pre-calculus with the fact that this is an even function, means it's supposed to be symmetric about the y-axis. My graph could be a little better, but it's good enough. Actually, I am going to go back and try to make that a little bit better. They're a little bit more symmetric about the y-axis. Now, as far as the derivative, all right. What we're going to consider now is think a little bit about slope, specifically tangent line slope. And I'm going to go ahead and draw some tangent lines on this graph. And I'm going to draw this in red. I'll put one right here. If I were to draw a tangent line that goes through 0, 0, I'm going to draw this in red. It's important to note that that line has a slope of 0. If I move over here maybe to the point 1, 1, the tangent line has a slope that's some positive value. Now don't worry, what is the numerical value? Not important for this discussion yet. And if I go over here to the point minus 1, 1, which is, roughly right there, and I draw in a tangent line, it might look something like this. Now, down below, I'm going to sketch just a real rough sketch of what I believe a graph of the slope of that function looks like. So let me go back to the first one. The first line I drew went through 0, 0. So the slope of the tangent line at that point is 0. So if this graph below, is a graph of the slope, slope of the first graph, it would go through the origin as well. Okay. Now, the second one I drew was this one. This was at x equals 1. Notice that the tangent line has a slope that's some positive number. The actual numerical value let's just say I don't know yet, but it's some positive value. I might put that maybe here. Now, if I go to the third line that I drew, and again, the intention was at x equals minus 1, you'll notice that the slope is negative. But hopefully my rough sketch is good enough to show that steepness-wise, it's the same as the first one. Or at least the graph seems to indicate that it is. So if I come over here on this graph, if this is, plus k being just some constant, the other one would be at minus k. So that other one would be maybe down here somewhere. And again, the second graph is a graph of the slope of this function. Now you'll notice that these appear to lie on a line, and in fact they do in this example. So if I'm to sketch it, it looks something like this. Now you'll notice that there's basically two different functions to consider on the board. We have, or on the screen, I've got the original function f of x, which is equal to x squared, and I've got a function now that describes its slope. I usually call that maybe s of x for slope as a function of x. You'll notice that the first function was quadratic, and then the second function is some linear function. This function right here is what we call a derivative. Okay? So, what is a derivative? Well, for starters, it's important to realize it is a function that gives slope of some other function. Now the million-dollar question here is, how do we find that thing? How do we find the derivative? And the answer is basically through what it is. Right? Again, the derivative is a slope. So what I'm going to do here is I'm going to take a moment and get rid of some stuff I don't need. Redraw my picture, and we'll talk about how we find that function called a derivative. I'm going to, in this example, stick with the function y equals x squared. I just want to get another sketch of it quick. Not super quick, but... And for this example, I don't need the entire thing. I'm just going to draw the right-hand side of it. It looks something like this. And again, this is the curve f of x equals x squared. Now, this derivative comes from the idea of slope, but it's important to realize it's slope of the tangent line. What I'm going to do is I'm going to pick a point here, right? X, f of x. And we're going to look for an equation that tells us the slope of the tangent line at this point. Now, slope from algebra class, y2 minus y1 over x2 minus x1. We typically need 2 points to calculate a slope. Right now I don't have 2 points, I have 1 point. So what I'll do is I'll just kind of imagine the second point. So imagine we move over a distance h. The new x value is x plus h. If we go up to our curve here, the new y value is f of x plus h. Now, by leaving this f of x and this f of x plus h, this language is basically good for any function. F of x in this example is equal to x squared. F of x plus h in this example is equal to x plus h, the quantity squared. Now what I'm going to do is I'm going to draw on the tangent line. I'm sorry, not the tangent line, the secant line. The secant line is the line that goes through the 2 points on my curve. Oops. I'm going to draw the secant line in blue. No, green. Green's a nice color. So there's the slope of the secant line, the slope of the line that goes through the 2 points. The tangent line, however, looks more like this. I'm going to draw that in red. An important thing to realize is that the tangent line, the red line, and the green line, they're not exactly the same, but they are close. They are curiously close. Now, I'm going to go ahead and write out an expression for the slope of the tangent line. That slope, as a function of x here, is approximately equal to the slope of the green line, which is equal to f of x plus h minus f of x over x plus h minus h. And I'm getting that from y2 minus y1 over x2 minus x1. But I'm going to go ahead and use this function here for my example. So that's going to be x plus h squared minus x squared over the difference between the two x values. If I take x plus h and subtract x, all I get is h. So what I have now is I have an equation here that gives me an approximation for the slope of the red line. You notice that it depends on h. Now, when these points are further and further and further apart, meaning if h is very large, the green slope and the red slope will get further and further apart. But when you go the other way, when h gets small, the red line and the green line will come together. So the smaller h is, the better the approximation. And we've got a mathematical tool to make that approximation perfect. We'll use the limit tool to drive this secant line slope to the tangent line slope. So the slope as a function of x is going to be identically equal to limit as h goes to 0 of this expression, x plus h squared minus x squared over h. And now it's just a matter of evaluating the limit. So I'm going to pick that up here because I need more room. Equals limit as h goes to 0. Now this can be expanded to x squared plus 2xh plus h squared. That's coming from taking x plus h times x plus h. And then we have this minus x squared that we don't want to forget about over h equals limit as h goes to 0. Now as I look at this numerator, x squared minus x squared, those are gone. 2xh survives, plus h squared also survives over h equals limit as h goes to 0. You'll notice that an h divides out of both terms. So we just get limit as h goes to 0 of 2x plus h. And when we take the limit as h goes to 0, this equals 2x. There's our function. Slope as a function of x equals 2x for the function y equals x squared. This is what we call a derivative. This is, or I sometimes call the slope function. This is the function that tells me the slope of our first function for any value of x. If I kind of go back and check it against the beginning of this where I drew some of the tangent lines. If you put 0 into this, you get 0 out. And if you go back in the previous in the video, you remember the slope of the tangent line was 0 at 0, 0. I tried to sketch the slope at x equals 1. You'll notice if you put a 1 here, we get 2, positive 2. I sketched the slope at x equals negative 1. Notice if you put negative 1 in, we get negative 2. Right? So this function is what we call a derivative. There's some language that goes with this that I'm going to chat about. So remember, this comes from slope. Slope is delta y over delta x. But when you write slope like that, this delta y, this means change in y. And when you write delta y, what you mean is a finite measurable change in y. When we take the limit as h goes to 0, these 2 points get closer and closer and closer together, and delta y goes to 0. The delta x also goes to 0, but the ratio went to the value 2x. Right? So when we set h to 0, the delta y becomes what we say infinitely small. It becomes what we call a differential. And the way we write the differential is dy. When h gets infinitely small, the delta x also becomes infinitely small. It becomes what we call a differential, and we write it dx. So this function, y equals 2x, in the language of calculus, we call this dy dx, which stands for differential of y over differential of x. The difference between dy over dx and delta y over delta x has to do basically with infinities. When delta x and delta y are measurable values, you can put a ruler to the graph and get numerical values for them. Dy is when h becomes infinitely small, therefore dy also infinitely small, and it becomes what is called a differential, an infinitely small change in y. Dx becomes an infinitely small change in x. So we would call this function dy dx, or it's called the derivative of y with respect to x. There's also a shorthand notation for it. This is sometimes shorthand as f prime of x, or y prime of x. So these are just 3 different ways of saying the same thing. Dy dx, f prime of x, y prime of x, all mean derivative of y with respect to x. Now, we're going to focus on how it's calculated and what it calculates. That's going to be the main focus for the rest of this course. For now, I'm going to talk about how it's calculated. So I'm going to go ahead and clear what I don't need. Oops. Get rid of all of this stuff. And write this in a more general way. Actually, we'll just do an entire new screen here. All right. So let's imagine now that we have some function, and it can be any function. I'll sketch a quick graph of it. Here's some function f of x. In general, to find the derivative of that function, you're imagining a point x, f of x. You're imagining moving over a distance h, so the new x value is now x plus h, and the new y value is now f of x plus h. Now this is written generically, so this is true for any value x, any function f. The slope of this line between these 2 points is at the heart of where the derivative comes from. So that's equal to f of x plus h minus f of x. That's true for any function, any value of x. divided by x2 minus x1. And again, when we take this x value, subtract this, we just get h. This ratio is called the difference quotient. You may have seen that in a pre-calculus class. They usually start introducing it in the course before calculus. And when we take the limit of this as h goes to 0, that's what the derivative is. So when we calculate derivatives like this, I call this calculating derivatives by definition. And the derivative of any function by definition is limit of f of x plus h minus f of x over h. Limit as h goes to 0. Right? I think what I'll do is I'm going to end this video now and make separate videos demonstrating how the derivative is calculated. So I hope this video does a reasonable job describing what a derivative is and gives you at least kind of a flavor for how it's calculated. Right? Have a great day.